Welcome to my lecture on probability. So we're going to begin with how do you calculate a probability. And it turns out there's two different ways. Okay. So one of them is theoretical, and in this situation it's the number of ways the event occurs divided by the total number of outcomes. In the other situation, in which you have data, and this is one of the most important ones, it's the number of times the event occurs in an observation. So how many times did you observe that outcome, divided by the total number of observations. And let's start out our example with probability with some observational data. Okay. So this data is on smoking and lung cancer. And this is a retrospective case-controlled study identifying 86 lung cancer patients and 86 controls without lung cancer and categorize them according to whether they were smokers or non-smokers. The goal here is to see whether the odds of lung cancer are greater for smokers than for non-smokers. Okay, so what this study did is they selected 86 lung cancer patients, 86 without lung cancer, and then they asked them, are you smoker or non-smoker? And we see that with the cancer, 83 of them are smokers, 3 of them are non-smokers. Okay, in the no cancer group are 72 smokers and 14 non-smokers. Okay, and if you wanted to look at this study a little bit more, it was done by this individual, H.F. Dorn, and I got the data from Ramsey and Schaefer. Okay. Now let's calculate some probabilities based on this data. So one thing that you should do is you should determine the total number of observations. So all that I did was I added up everyone here. So I took 83 plus 72 plus 3 plus 72. That's the total number of participants in the study. Or I could have done 86 plus 86 and I get 172. Okay, that's going to be the total number of individuals in my study. Now, according to this data, the probability someone randomly chosen in this study is smoking and is a smoker and has cancer is going to be the observed number, 83, divided by the total number of observations, which is the 172. So there's a 48% chance that an individual lies in that one cell of smoking and cancer. Okay. Now the probability of being a non-smoker and having cancer, there were only 3 individuals here that were non-smokers and had cancer. So that is going to be 1.74%. Now, the odds someone is a smoker, well, you can have cancer and be a smoker, or you cannot have cancer and be a smoker. And you'll get this 83 plus 72 over 172, or 90%. Okay. So 90% of the people in the study are going to be smokers, so only 10% are non-smokers. And the proportion with cancer, well, we designed the study so that only 50% of them had cancer. Okay, remember 86 with cancer, 86 without. Okay. Okay, well, here's a few more calculations. So this is going to be one of our first examples of the general addition rule, and that is to calculate the probability someone is a smoker or has cancer in the study. And this statistic might represent the proportion or demographic of individuals who are at risk. Okay. So smoking or cancer, that probability, you go back to the table, 83 smokers, or you could be a smoker and not have cancer, so plus 72, or you could have cancer and not smoke, there's only 3 of them. Okay. So we'll do 3 plus 83 plus 72. That was the data that I showed, divided by 172. That's 92% basically. Okay. And I apologize, that doesn't belong there. So that 91.8%, I can break this up into another way. This could be the probability of smoking. That's 83 plus 72. So I add all this up. So that's probability of smoker. Then I could do probability cancer. 83 plus 3. I apologize. 83 plus 3. But notice I've counted 83 one too many times. So here's an 83, here's an 83. It only occurs once over there. So I'm going to subtract it. Minus 83 over 172. And this is equal to the probability of cancer plus the probability of smoking minus the probability of smoking and cancer. And this illustrates the general addition rule. This general addition rule says probability of A or B is equal to probability of A plus probability of B minus the probability of both A and B. Okay. So this rule is something that you will have some homework exercises on, and it's important to keep in mind. Okay. So that's called the general addition rule. Okay. Now, the next rule I'd like to talk about is the complement rule. Okay. Now, the complement rule are all outcomes, and I want to stress that they're all, not just one, because that's the common fallacy, is someone will just select one way in which the event is false. But the complement is all outcomes that make A false, and that's denoted by A complement. And the complement rule says this: the probability of A is equal to 1 minus the probability of its complementary event. So for instance, the probability of smoker, we did this calculation before, that was the 90.11%. That's equal to the same as 1 minus the probability of being a non-smoker. And that will be 1 minus 3 plus 14 divided by 172. That's again going to be this 90.11%. So whether you calculate it directly or you use the complement rule, notice you get the same answer. Okay. Now, the probability of being non-smoker or no cancer, well, the complement rule makes this easier to calculate, because if I want to calculate probability of non-smoker or no cancer, I could use the general addition rule, and that'd say what are the odds of being a smoker and no cancer, or non-smoker and cancer, or non-smoker and no cancer. Or I could just do 1 minus the probability of being a smoker and having cancer. Okay. And this last one is much easier to calculate rather than having to add up all those other probabilities. So sometimes it's more convenient to use the complement rule. So a concept in statistics is independence. And it asks this: does smoking affect lung cancer? And from a statistical point of view, the question asks if smoking status affects the probability of lung cancer. In other words, are smoking and lung cancer independent or dependent events? Okay. So what does it mean to be independent? Well, two events are independent if the probability of A and B, you can just multiply them. The probability of having both occurs in the proportions of A and in the proportions of B. Otherwise, they're dependent. Okay. Now, when I say equals here, I mean that with air quotes, because when you have observed data, there's going to be random chance involved. And these two quantities may not be exactly equal on the dot, but are they roughly equal, or are they very unlikely to be equal? Okay. Well, let's do this calculation. The probability of being a smoker, well, there's 83 that have cancer, 72 that don't, divided by 172 observations, and 90% chance of being a smoker. Probability of cancer is 50%, but that was by design. Okay. Now, the probability of smoking and cancer that was observed, there were 83 that had smoking and cancer. Out of 172, that's 48.24. If smoking and cancer are independent, I can just multiply them. And I do that here. That's 45%. Now, 45%, the question you should be asking yourself, is 45% approximately 48%? Would one observation here or there, being a different category, affect it? And if so, by how much? But as you can see, or you probably guessed, 45%, one or two observations going in a different category isn't quite going to bump you up to 45%. So, like, if this was, instead of being 48%, if this was more like 46 or 45.5%, maybe I'd be more okay saying that they're independent. But because these two numbers don't seem to be equal by random chance, I'm going to say that they are dependent. So, in summary, probability of smoking and cancer does not equal probability of smoker times probability of cancer. And that calculation tells me that these two are dependent. Your smoking status has an effect on your cancer status, according to the observational study. And notice that this study is observational. I cannot claim causation. And it's also impossible to form a study that would be in a designed experiment which allows causation, because it's unethical to assign individuals to being in a smoking group versus a non-smoking group. And there are now ethical standards in data collection that apply to the medical fields, psychology, any data collection. Okay, so we cannot design this experiment. Okay. Now, I'd like to point out what we have is we started with a table, and these tables are also often called contingency tables. And the types of data that we're dealing with is when we have an input variable that is categorical or discrete, and the input variable is explanatory and discrete. Okay, and our input variable was if they were smoking or non-smoking in this example, and our response was if they had cancer or non-cancer. Now, this is not going to be on your homework, but I'm just including it for your reference because it completes the data analysis, but it's not in your textbook. The odds of cancer for smokers, well, that's going to be this 83 divided by 72, right? If we go back to our data, our odds for cancer, if you're a smoker, 83 of them have cancer, 72 do not. And we can do the same for non-smokers, 3 divided by 14. And we can compare the odds, okay? So 3 divided by 14 is 0.21. These two numbers are quite different. Like, the odds are quite higher for smokers versus non-smokers of cancer. And how much more likely you are to suffer from cancer if you're a smoker versus non-smoker is the ratio. 1.15 divided by 0.21. That's equal to 5.47. That indicates your odds of having cancer are 5.5 times greater if you're a smoker versus a non-smoker. Okay, and that's why there's convincing evidence of that smoking causes cancer, or at least lung cancer, even though we can't have it designed experiments. Okay, so our conclusion is that there's convincing evidence of lung cancer being greater for smokers or non-smokers, for smokers compared to non-smokers. Okay. But as this is a retrospective observational study, we cannot address if smoking causes lung cancer. It's just that the evidence is so overwhelming. Okay. Now, one carefully worded thing here that I want to read to you. It says inference to the wider population is only appropriate to the extent that the sample of cancer patients and controls constitutes a random sample from the population with and without cancer. And that sounds like a legal wording here. And in fact, it is in a statistical form. It says that as if this is a random sample, this is the extent to which smokers are more likely to have lung cancer than non-smokers. And they're saying that this is hinged on it being representative of the population. They haven't assessed if it is a representative sample from the population, which is a much harder question to assess. Okay, so here's an example, and it says in a certain population, 10% of the population has disease A, 15% has disease B, and 5% has both. What is the probability a randomly selected person in this population has disease A or B? Well, that or should indicate that you use the general addition rule. This is the general addition rule. And all we have to do is write down probability of A, well, that's 10%, plus probability of B, 15%, and subtract what they have in common. That's 5%. So 20% of the population is at risk for having one of these two diseases. They might be what you call in the at-risk category or infected category, actually. Okay, so that's quite worrisome. Now, you might be asking what proportion of the population only has disease B. Maybe disease B is treatable and you like to target them. Well, all you have to do is subtract the intersection. You take disease B and you subtract the proportion that has both. So 15 minus 5 gives you 10%. And how this works is that probability of B, if you really want to know why we can do this, probability B breaks down into the probability, into the event that someone has disease B and not A, plus the probability they have B and A. Okay, so we can just solve for having B and not A. So probability of not having disease A is 1 minus, okay, so different question, my apologies, I got it mixed up here for a second. So here's a second question. What proportion of the population does not have disease A? And you say 90%, okay? And that's just using the complement rule. Probability of not having disease A is 1 minus the probability of A, okay? Okay, here's another question. It says a test is devised to detect if an individual has a disease, and 8% of the time it diagnoses the individual incorrectly. Okay, unfortunate, but sometimes that happens. If 100 individuals are tested, what are the odds that at least one test is diagnosed incorrectly out of the 100? And I stress out of the 100 because it is a different probability for a group of people versus an individual. We're told for an individual it's 8%. So probability at least one test is incorrect, I'm going to use the complement rule. The probability at least one incorrect is 1 minus the probability of the complement. Well, what makes at least one test incorrect is that all of them are correct. So this boils down to 1 minus the probability of the first is correct, and the second is correct, and the third is correct, etc., all the way to the 100th. Now we can use independence. It's unlikely that one individual's outcome affects another. It's possible, but unlikely. So independence is a reasonable assumption, especially in a large population. Okay. And so if we use independence or assume independence, it's going to be 1 minus the probability the first is correct times the probability the second is correct. And we multiply all of them all the way to the 100th is correct. Now the probability the test is correct is 92% because we know 8% of the time the test is incorrect. So using the complement rule, we get 92%. 100 minus 8%. Okay, gives me 92%. So 1 minus 92 to the 100th power, that gives me a 99.97% chance that at least one test is incorrect out of 100. Okay, so notice that this is not the original 8%. Okay. Now, here's an application in circuitry, and we all have electronic devices, and there are circuit components. So you can imagine that this is a little component that works within your electronic device, within your computer, what have you. And here we have a voltage being applied, and we have 3 resistors, okay? And this is an example of series versus parallel design, okay? So here's the question about the circuit. We have a current flowing, and it goes to the 3 resistors. And in order for it to go to the point B, at least one of these resistors has to work. Okay? If the first one works, it gets to B. If the second one works, it gets to B. If the third one works, it gets to B. If all of them do not work, it doesn't get to B. Okay? So we have the diagram. Okay? And it says each resistor has an 80% chance of working. And we know that, these resistors, they operate independently. If one resistor fails, that doesn't mean that the other one automatically fails. It might fail later, but it's not going to fail because the other one failed right away. Okay? It is reasonable to assume the condition of working or not working for each resistor is independent. And the question is, was the probability all resistors are working? Well, if I was to ask that, not working, but defective, so I apologize. Okay, so was the probability all resistors are defective? That's if all are defective, that means the first is defective and the second is defective and the third is defective. Now, because we said that they're independent, I'm just going to multiply their probabilities, which is going to be 0.2 3 times, so 0.2 to the third power, and that's 0.008 or 0.8%. Now I'm going to ask you, what's the probability the circuit is not working? Well, the circuit is, the probability the circuit is working is going to be the probability the circuit is working is the probability at least one resistor is working, so that electricity can get from point A to point B. And that's going to be 1 minus the probability of the complementary event. So I'm going to use the complement rule. So the opposite of at least one resistor is working is the probability all resistors are defective. And 1 minus that is 1 minus 0.008, or 99.2% chance. Okay, so it's important to do these calculations so that companies don't have a large number of returns and so that people will want to purchase their products. Okay, now I want to emphasize that we did this calculation. Probability all resistors are defective was done up here. Probability all are defective. Okay. Now here's an example, not of dice, but of tossing a coin. Okay. And this should be coin, so I apologize. Okay. And so we're going to toss 2 coins, and I'm going to ask you, what is a sample space? Now, I'm going to go back to our calculations of probability. Okay. We're now dealing with a theoretical probability. This has not been observed. Okay, so we're going to use this theoretical calculation of probability, and we need to know the number of ways the event occurs and the total number of outcomes. Total number of outcomes is related to something called the sample space. So here we have our sample space, and the sample space is just the set of all possible outcomes. So we have our outcome for die 1 and our outcome for die 2. So die 1 could be heads, die 1 could be tails. Okay. Die 2 could be heads, die 2 could be tails. So I'm going to denote these outcomes. The first one is both are heads. Then here the outcome is heads, tails. First heads, second tails. Tails, heads, and then tails, tails. Okay, so that is the sample space for 2 coins. If you do it for 3 coins, there's a third die that needs to be considered. Okay. Now, an event A is any subset of the sample space, and we can compute probabilities of events. Okay. The complementary event is the set of all outcomes in the sample space that are not in A. They're also the statements that make A false. The intersection of A with B is called A and B, and this corresponds to an AND probability. The union of A with B is the set of all events that are either in A or B and is an OR probability. Okay, and you'll see these things often. Okay, so I apologize, I'll change that to coin example. So A is the event that there is exactly of 1 head in 2 tosses of the coin. B is the event the first coin lands heads. So A is going to be exactly 1 head, so there's heads, tails, or tails, heads. That's a subset of the sample space. The complementary events are the things in A that are not, the things in the sample space that are not in A. So the sample space is this. This is outcome in A, this is outcome in A. So the things not in A are heads, heads, and tails, tails. Okay. B is going to be the event the first coin lands heads, so that's heads, tails, and heads, heads. Again, subset of the sample space. And if I want to figure out what is A and B, well, if I look here, heads, tails, this outcome right here, is shared in B and none other. So it's just that single event. A or B is all the events in A or B, so heads, tails, tails, heads. Then right, heads, tails already counted, so I don't need to count it again, so I'll just throw in that one, heads, heads. Okay. Now, probability of A is 2 out of 4. There are 2 events in A out of 4 possible outcomes. Probability of B is 2 out of 4 as well. Probability of A complement is 2 out of 4, or 1 minus the complementary event, which is again 2 out of 4. Probability of A and B, well, that's 1 outcome out of 4 possible ones. And probability of A or B, well, we saw 3 outcomes out of 4. And we can also do the complement rule. Probability of A is 2/4. Probability of B is 2/4 minus the intersection, which is 1/4. So we get 3/4 either way we do that. Now here's an analogous experiment, and it's in genetics. And this is by a guy named MENDEL. And he was a monk, and he studied mathematics and biology, and he went on to become a science teacher. Now, for 8 years in 1957, he studied peas and he grew them in his garden, and he pollinated the plants, saved the seeds to plants separately, and analyzed the succeeding generations. He self-pollinated the plants until they bred true, giving rise to similar characteristics generation after generation. He studied easily distinguishable characteristics like color and texture of the peas and flowers. And this ultimately led up to the development of genes and genetics, heredity, how it's passed on in biology. Okay, and when he crossbred true breeding lines with one another, he noticed something interesting. The characteristics of the offspring consistently showed a 3-to-1 ratio in the second generation. Okay. So let's take Keller as an example. And Mendel showed that when a true breeding yellow pea and a true breeding green pea were crossed, their offspring always produced a yellow seed. However, in the next generation, the green peas reappeared at a ratio of 1 green to 3 yellow. And to explain this phenomenon, Mendel coined the term recessive and dominant traits. Okay. The green trait, which seems to have vanished in the first generation, is recessive, and now yellow is dominant. And he published his work in 1966 of these invisible actions, which are now called genes. So let's look at this diagram. This is what's called a dihybrid cross. And here are the gametes from the heterozygous parent and gametes from another heterozygous parent. So this has YR combinations, and when you breed it with a YR, you only get yellow round. Okay. Here is YR, but this lowercase y means it's not dominant. Okay. So we have a YR, we get another YR. YYRR. Okay. And these are the outcomes. This is the sample space of events for the dihybrid crosses. These are all possible outcomes. What Mendel noticed is, hey, look, sometimes I can breed this YR with another YR, and I'm going to get a YYRR, and it comes out green. Okay. And then here I can breed this, and it's not round. Okay. And so this comes from a YR bred with another YR with a non-dominant R. Okay. And here I can get a non-round and a green that's bred from a YR in which they're both lowercase or non-dominant Y and R's. Okay. So non-round and not yellow occurs here. And he saw that there are these certain ratios. Okay. So let's talk about this. So based on the sample space, what is the probability a pea pod has a green offspring? So if I go to the sample space, notice the sample space is 4 down and 4 across, so 16 possible outcomes. And I ask for the probability of a green offspring. So 1, 2, 3, 4. Its probability is 4/16, or a 1/4 probability. I can ask you, what's the probability a pea pod crossed at random is wrinkled? So how many of these are wrinkled? All of these 4 are wrinkled. So it's again 4/16 or 1/4. Well, what's the probability it's green and wrinkled? That's much less common. There's only one way to get a green wrinkled one, okay? And that's 1/16. Okay. Now, just to review some probabilities, I could ask you, was the probability a pea pod crossed at random is green or wrinkled? So probability green plus probability wrinkled minus the probability of both is 4/16 plus 4/16 minus 1/16, so 7/16. And was the probability of pea pod crossed at random is not wrinkled? Well, let's do 1 minus the probability of wrinkled. So 1 minus 1/4. So there's a 3/4 probability. Okay. So I just wanted to reiterate, independence means that knowing a trait of the population does not change the odds of the population. So, for example, if sex and gender are independent of job assessment promotion, the probability of promotion does not change based on sex or gender. And from time to time, we might use this equivalent form of independence. And that equivalent form says this. It says probability of A given B, okay, is equal to probability of A. That's the equivalent definition of independence. It says the probability of A does not change based on B if A and B are independent. B should not affect the probability of A, so knowing if B occurs doesn't change the probability. So in this context, if A is promotion and B is the gender or sex of an individual, the probability of promotion given the individual's male or female should not be affected by the given information. So it's just equal to the probability of promotion. Okay, and that's what independence means. That sex or gender would not affect the odds of promotion. Okay, well, thank you for joining me. That's our topic on probability. See you all later.